Dr. Vinti, the platform is yours now.
We start, Dr.
Yes, we can start.
Okay. So today we have less number of participants, it seems.
No, I hope they will join in this
Okay.
webinar.
Okay. Okay. So just to sort of understand from everybody, how are you feeling right now at this moment with whatever that has been done? Good. Okay. So did everybody figure out the binomial distribution and the Poisson distribution? Or at least, if not 100%, then maybe even 50% is good. It's passing percentage. Okay, you got the book you recommended. Okay, fine. Which one was it?
You're on mute.
I can't hear you, Dr. Biju. Okay, I can't hear Dr. Biju. Okay.
Yes, madam, this one.
Yes, it's a good book. This is the one that I'm using actually.
Yeah.
Okay.
So
It's the book that I'm using. So anybody wants any clarifications and stuff, right? Please go ahead and read this book. What we do is try and simplify it, but yeah, it's a pretty comprehensive book, right?
yeah, at least we can learn the basics from that.
Yeah, right. So it's a, I mean, there are many biostatistics books. I mean, if you start off, there's a huge amount of stuff that is there. Okay. So today, what we're going to do is something called normal distribution. Okay. So today, first we'll just look at looking at how a probability distribution and this normal distribution works. Then we'll go down to something like a sampling distribution. Okay. And then we'll go on to confidence intervals. Okay. And then if we have time, we'll go to t-test. Okay. So today we'll just start with something which is called a normal distribution. Okay. So earlier we did something like a binomial distribution and a Poisson distribution. Now both binomial and Poisson distributions were discrete distributions, right? So you knew that those were like you had X number of occurrences or a proportion, proportion of success, right? So that was those kind of distributions. Whereas in a normal distribution, so you are looking at something which is like a continuous distribution. Okay. So I'm just going to share my screen. Okay. Okay. Just 1 sec. Okay. Can you see my screen now?
Yes,
Can
yes.
everybody see my screen? Okay. Now these are the characteristics about the normal distribution. Okay. Now the normal distribution you would have read, it's like a curve. Okay, it's like a cylindrical kind of a curve. So it is symmetrical about the mean. Okay, and it is the curve on either side of mu. Right, mu is a is what is the indication of a population mean. Okay, now sometimes you don't have normal distributions, you can always standardize it, but we'll come to that later. Okay, in this case, in a normal distribution, the mean, the median and the mode are all equal. Okay, Now the total area under the curve above the x-axis is 1 square unit. Now this represents, when I say 1 square unit, it means the total probability is always equal to 1. So on one side of the curve, you will have 0.5 probability, and the other side you will have another 0.5. So the total is always equal to 1. Okay, so because, as you said, it says because the symmetry already mentioned, 50% of the area to the right of the perpendicular erected is at the mean and 50% is to the left. Okay, now if we erect perpendiculars a distance of 1 standard. Now anybody else done something, has understands 6 sigma? Why do you say 6 sigma? So 6 sigma means 3 standard deviations to the right and 3 standard deviations to the left. Okay, so in a normal distribution, the entire probability can be divided into 6 distributions to 6 sigmas, where 3 is on the right hand side and 3 is on the left hand side. So when we erect perpendiculars, a distance of 1 standard deviation from the mean in both directions represents 68% of the total area, or 0.68 probability. If you look at 2 standard deviations, then it represents 0.95% or 0.95% of the probability. And if you look at 3 standard deviations, will cause approximately 99.7% of the total area to be enclosed. Okay, there will be a little bit here and there, but broadly within 3 standard deviations, right, or to the right, and within 3 on the left, right, you will have the entire probability that can be represented. Okay, now the normal distribution is completely determined by the parameters mu and sigma. Right, now here we are saying mu is for the population and sigma is for the standard deviation. Okay, so we have not come to sample size right now, but right, this is what we are looking right now. Now, in other words, a different normal distribution. So if you have a different value of mu or standard deviation, okay, the shape of the distribution will shift. Okay, now different values. Okay, so because of the characteristics of these two parameters, it is often referred to as mu is the location parameter and sigma is referred to as a shape parameter. Okay, so if I go to the next, okay, now here you can see this. Okay, now these are the shapes. So you can see 1 standard deviation and 1 standard deviation, that is mu minus 1 standard deviation and mu plus standard represents 68% of the area, right? So this is 0.68 probability. If you go to 2 and 2, then it is 0.95. Okay, and you will see in the tails you will have 0.025 left. Okay, and this is also, you need to understand this, because even when you do confidence intervals, then you also need to understand this, right? And if you go on to 3 standard deviations, then in your tails you will have only 0.0015, but between this 0.997 you have pretty much covered the entire normal distribution. Okay, here you will find, okay, that the mu has changed, but the standard deviation is the same, right? You will notice in this case the standard deviation is the same, but in this curve you will find the mean is the same, but the standard deviation varies. Okay, so depending on the values of mu and standard deviation, your shape and distribution of your normal distribution is going to change. Okay, so every parameter that you will have, depending on whatever is the respective mu and standard deviation, you will have a different shape. Okay, now in a standard normal distribution, okay, as it is sometimes called, it has a mean of 0 and a standard deviation of 1. Okay, so this is something what we call when we standardize our distributions. Okay, so we will this is a Z score. You know, when you standardize, you convert each of it into a Z score. Okay, because if you want to find the probability, so whatever values that you have, you will tend to convert into a Z score. So Z is actually called a Z score. Okay, now let's just take an example. Okay, Now, the uptimer is a custom made lightweight battery operated. I have taken the examples from this book only, so that if you pick up these books, it will be easier for you. Okay. That records the amount of time an individual spends in the upright position. In a study of children ages 8 to 15 years, right, they studied 529 normally developing children who each wore the uptimer continuously for a 24-hour period. Okay, so what are they studying? They're looking at the amount of time an individual spends in the upright position, right? And the study was on children 8 to 15 years. What was the sample? It was 529. Okay, now they found that the amount of time the children spent in the upright position followed a normal distribution with a mean of 5.4 hours. The mean is 5.4 hours and a standard deviation of 1.3. Now, assuming that this finding applies to all children 8 to 15 years, okay, find the probability that a child at random spends less than 3 hours in the upright position in a 24-hour period. Okay, now you are saying the mean is 5.4. Okay, and you want to find out the probability that the child selected at random spends less than 3 hours. Now you know the entire curve is in terms of a probability, which is the total probability is equal to 1. Okay, now you have to convert this into a Z score. So when I have to convert this into a Z score, it is simply 5.4 minus 3 divided by the standard deviation. Okay, as you said, if I go back, okay, this is how I do my Z score. Can everybody see this? X minus mu divided by the standard deviation. Now in this case, X is what? 3, mu is 5.4 and sigma is 1.3. Okay, now you don't always have to calculate because we always have a calculator that we have. Okay, so we are going to use this calculator. Okay, okay, I have this calculator, so let me just give this calculator to you guys. Okay, can everybody see my screen? Can you see this
Yes,
calculator screen? Okay.
Yes.
Now let us try and do this calculation. What is my raw score? It is 3, right? What is my population mean? It is 5.4. Okay, what is my standard deviation? Agreed? Okay. Eyes are not coming. Sorry, 5.4. It is 5.4. Okay. So what have I got? I have got a Z score of minus 1.84. Okay. Now, if you look at this curve, okay, what does my question says? My question says, if I go back, my question says, find the probability that a child selected at random spends less than 3 hours. Okay. Now I want to calculate this area. Right? Can you see this area, which is a shaded area?
Be-
One sec again. I've lost the calculator now. It's in the, okay, this is it. Yeah. Okay. Can you see my screen?
Not the calculator, but the other PowerPoint.
Let me just see one sec. Okay. Okay. Now I am looking at this part. Okay. I'm looking at less than 3. So what is my probability is going to be 0.03. And what would my probability if it had been more than 3? it would have been 1 minus 0.03. Right? If it had been something like, what is the probability between 3 and 5.4, would have been 0.46757, that is 0.5. Right? Can everybody take out a piece of paper or something of that sort? Right? And we'll go to 2 decimal places. Okay, so let us assume that my probability for less than 3 is 0.03. So what will be more than 3? Can you just subtract 1 minus 0.032? What do you get? What answer do you get? What is the answer that you get?
0.68.
1. That is total 1 minus 0.032.
0.032. Yes, madam. So it's
It should be 0.96.
0.968.
96. Yeah, sorry, 968.
Yeah, right. So you need to understand, because it says less than 3, so I looked at the tail part of it. Okay, as long as you understand what is being asked, you can do everything. You don't have to calculate, but you need to understand, and you need to draw that distribution and say, figure out where do you want to do. Right? How does the question work out? If I had said, what is the probability of 3 less than 5.4? Now you know my 5.4 is at the 0.5 level. Okay, it is in the middle, the center. That is at 0.5 probability. So 0.5 minus 0.03 is what? 0.5 minus 0.032. What is it?
Point 468.
0.468.
Right? So this is exactly where you can see out here 0.468 or whatever. Yeah. Right? Just to round out. Okay.
Windy, where did you get this 0.0324?
So this is the probability was 0.032 was this, right? Because I looked at the Z score. Okay. Now let me just see. Let me just share with you a Z score table. Let me just see downloads. Okay. Can everybody see this?
Now, Windy, we are seeing that score.
Can you see the standard normal distribution?
No.
We are seeing the Z score calculator.
One sec, let me just again share. Okay. Okay, can you see this?
Yeah.
Okay,
Yeah.
great. So now when you say minus 185, okay, now if I go to minus 185, this is a Z distribution table. Okay, so you on the top hand side, you will say 0.00, 0.01, 0.02, right? So if I go to minus 185, that is here, this column, right? If I go to this minus 185, I will get the same value. This is a Z table. This is, you can find these tables, ready-made tables there also. Right? So you can look at this value there also. Okay. So the idea was, okay, because you are looking at the Z score level of 185. Okay. So a Z, because, if you just, sort of kind of understand this. Okay. I'll again, kind of share screen. Okay. So if you look at this entire curve, okay, is 1. Okay. Now I have divided this into three standard deviations on this side and 3 standard deviations on this side. Okay. Now
There is
if I am
nothing.
can you see my screen?
No.
No, madam.
Okay, sorry. Okay. Now can you see the screen? Yeah. Okay.
Yes.
So if you look at this, okay. Now what we have studied is that when I have this 5.4 in the middle, okay, my entire distribution is 3 standard deviations on the right of 5.4 and 3 on the left. Okay, so what I have done is basically now this 3 minus 5.4, I have converted into a Z score. Okay. And as I said, my Z score is basically my standard deviations. Okay. So this is a Z score is this is minus 1.85. This is almost two standard deviations, it's like that particular score divided by my standard deviation. This is my Z score. Okay. Now my Z score will basically tell me that on my probability distribution, right, at what level of probability am I at? Is everybody clear with this? It's basically I have converted this into a probability distribution. Okay, and as you can see, these variables are like, when I'm saying 5.4 hours, now this is like an interval scale. Okay, it's a continuous my data is continuous. So I can convert a continuous data into a probability range. Does this make sense or does this not make sense? I'm stopping share for a moment. Okay, does this make sense or does this not make sense?
Will you please explain mu, delta, mu, sigma, plus mu?
Okay, so let me just again describe this. Okay, so when you talk about, let's say, rainfall, okay, now let's say you have a rainfall between, let's say, 30 centimeter in Kerala over, what is the maximum rainfall that you will have, Dr. Sunil Kumar, in Kerala?
Oh, I don't know.
Nobody knows?
Yeah, let's
Okay,
take 48.
maybe I'm just saying, let's say 100 centimeters. Okay, now, and let's say I have done this kind of distribution over many number of years, where I have calculated that, okay, let's across the monsoons, and the monsoons in, let's say, 3 months, okay, the rainfall can extend from this figure to this figure. Okay, and I have made this distribution, like it's like a histogram. Okay, now I want to know that, and it's obviously I have done this maybe over 20 years. Okay, and I want to know basically that what is the probability that I will have rainfall between 70 centimeter to 100 centimeter. Okay, now because I have constructed a probability distribution, okay, and I have done this, if you remember the last time we did this frequency distribution. So anytime I had a figure, then I would convert it into a frequency, and then I would sort of make it into a probability, and I can just map the probability, right? Right, and it becomes like a frequency curve. But here in this case, my frequency curve is like a normal distribution. Okay, I wish I had a chart or something, and I could have actually shown this to you. Okay, let me just see if I can do a paintbrush. Okay, let me just see if I can do, okay, let me do an Excel sheet. So we start with an Excel sheet. This, you need to first relate to this, otherwise it becomes difficult. Okay, let us just screen. Here it is. Okay, can you see my Excel sheet? Okay,
Yes, ma'am.
so let's say I'd say I had year. Okay, just to kind of make you understand. Okay, right, I had year, and okay, so let's say I did from 1951 onwards, 1952. Okay, and let's say till 2002. Okay, right, I'll just go on like this, just for the sake of just showing you that I want to do this. Okay, and let's say assume can you can all see my screen, right?
नहीं तुम कुछ तो कर
तुमको क्या करने का बहुत तुम अपना काम करो तुम अपना काम करेगा तो हम
Here, this is the rainfall. Okay. So somewhere 30 centimeter, somewhere 20 centimeter, right? 50 centimeter, 70 centimeter, right? 56 centimeter, 28 centimeter, 12 centimeter, 75 centimeter, something like this, right? Now what will happen out this, okay? So now what I can do based on all this, let's say I have something like 20, 30, 40, 50, 60, 70, 80, 90, 100. Okay. And let's say in 20 years, I had, let's say I'm looking at a sample of 30 years. In 30 years, 20 centimeters was 5 times. This was 2 times. This was 7 times. This was 2 times. This was 4 times. This was 5 times. Okay. This was again 2 times. Okay. Okay. This was 1. This was 1. Okay. Total is, okay, this is 3. Okay. So this is total is 30, right? Fine. Total is 30. Okay. Now what have I done out here is now I can take a distribution of this of 30. I have got a probability. I have converted this into a probability. True? Right? And if I put this into a cumulative frequency, this will become everybody okay with this? Right? Now, if I plot this in a normal distribution, it will look the same thing like this. Will it look like this? Can everybody see my screen?
No, but
That's
this is not continuous data, no. This is frequency.
Yeah, I know this is not continuous. Okay, obviously this is not continuous. I'm just giving you an example. But let us assume that this was continuous. Okay, let us assume that when I make a standard normal distribution, what I do is I standardize the scores. And I standardize the scores and I say, when I say x minus mu divided by standard deviation, I convert it into a normal distribution. Okay, so it is always possible to have a slightly non-normal distribution and convert it into a normal distribution, which looks like this. Okay, and this is how then in a normal distribution, I use an assumption to calculate my probability. Okay, so this is an assumption that we do, right? So we assume that this is a standardized normal distribution. Of course, in life, you will never find a perfect normal distribution, but if you have a large, when they say you have a large enough sample, okay, or a population size, and if you increase the frequencies, what you will get is something like a normal distribution. And if you standardize it, this is the kind of shape that you will get. All good till here?
maybe we are seeing the Excel, not the graph.
I didn't get what you said, Dr. Sunil.
No, we were seeing the Excel. Not
Yeah,
the,
I was just trying to demonstrate, like, how you can sort of do it. Okay, we are not saying that you do it. Okay, I'm just trying to relate that, a normal rainfall, okay, you were converted into a frequency distribution and you put it in a cumulative distribution. But suppose you kind of plot it like it will, like you have a, total probability is equal to 1. It's the same thing. It's pretty much the same thing, except that you have a large number of observations. So the curve looks like the normal distribution. Okay. And because the curve looks like the normal distribution, you can use Z scores because you've standardized the distribution by doing X minus mu divided by standard deviation. So it becomes, it's like converting it into a benchmark of 3 standard deviations and 3 plus minus X plus 3 minus plus minus 3 distributions. Okay, so that normal distribution score, so you can use the Z score to calculate your probability. Right, so what is Z? Right, Z says Z is equal to X minus mu divided by the standard deviation. So you are looking at the difference between X and mu, and you are looking at it in terms of the, the standard deviation. So you are kind of converting it into a score, and that is how you kind of do this. Okay, let's look at a couple of, this is not going to come, day one. Okay, let's try and do, one more example. Okay, let's look at this example. Okay. And let's see if you guys can do this. Okay, can you everybody see my screen? Okay, and you have a calculator with you. Now if the total pain scores for a certain population, and I've just made up this question, I obviously didn't have an example, okay, but I just kind of made this question. If the total pain scores for a certain population approximately normal distributed with a mean of 55 and a standard deviation of 15, okay, find the probability that an individual picked at random will not picked at random will have a pain value, not a cholesterol level, but have a pain value of between 30 and 80, greater than 75, less than 50, between 70 and 95. Okay, so how are we going to do it? Okay, how are we going to do it? Can we use a calculator? Okay, what did I have? Between 30 and 80. Okay, how do I assume that the pain level that a person will have if I pick up an individual picked at random from this population will have a pain value between 30 and 80? Okay, so in this case, okay, my mean is what?
55.
30 minus 55
Okay,
divided by 50.
my raw score is, mean is what? What is my population mean is? 55. Standard deviation is 15. Okay, and the first one I've said is 30 and 85. So what is the value that I'm getting out here? It is minus 0.166. Okay, so what is the value?
Are you doing it somewhere in the calculator?
Can you see my screen or not?
No.
We cannot see the calculator.
Okay, one sec. I don't know what is this business of, okay. Okay, so here is what I had. Okay, I had a mean. My mean was 55. My standard deviation was 15. Okay, so I put in these values. Okay, mean was 55, and I wanted a value between 30 and what is the probability that a person walking into my clinic will have a probability of a pain between 30 and let's say 85. Okay, so first I will take out 30. Okay, and what is my Z value out here? It is minus 1.6667. Okay, and if I look at my probability level from here, right, less than 30 is, at 30 is 0.4779, right? So let me can somebody just park this figure as 0.4779 somewhere? Can somebody just park it, just write it somewhere or put it in the chat box?
Yes.
Now what I'm going to do is 85. Now I'm going to look at 85. Okay, so I'm going to do now 85. Okay, now what happens to my Z score out here? Now it becomes a +2. and here it says it is 0.97725. Okay, now can anybody put this figure of 0.97725 in the chat box? Okay, now the difference, the probability that is there between 30 and 85 is going to be the difference between the probability of 0.97725 and 0.04779, right? So the probability that a person walking into your clinic will have a pain score of between 30 to 85 is going to be between, it is going to be 0.97725 minus
779.
0.04779. Okay, right? So you'll have to calculate this. Sorry, I put comma instead of point. Okay, so if you find out a difference, then that is the probability of people having that pain level, right? Now suppose I say, what is the probability of people having a value of a pain of more than 80? Okay, now in this case, let's say I put 80 out here. Okay, now if I look at my 80, okay, now the value till 80, the value can see. Okay, now you can see that it is 1666, and you can see the value is, the p value till 80 is 0.95. Now what is it that I want? I want the probability that people are going to suffer from more than 80 pain value. In that case, my probability is going to be 1 minus 0.955221. Okay, that would be my probability. That is equivalent to 0.04779. Okay, so you can try different permutations, combinations, etc., etc. But this is the underlying logic in terms of using a standard normal distribution. Now, this is the most popular distribution that you have, right? So even in those distributions which are, not relatively continuous distributions, which are not, I would say, follow a normal distribution, you can always standardize your values and convert it into a normal distribution so that you can use the normal distribution to calculate your probabilities. Okay, would you want to try one or two or more, or we can
I
go
have one question. Like in our general sample in our study, how to come to that value of standard deviation?
how to so normally it is how to come to this. In this case, for example, I had given this rain thing. Okay, I can calculate the standard deviation, no? Right, in this value, right?
We cannot see the screen.
Right, so I have, can you see my screen?
Yeah,
Right, I'm just looking at, let's see these here. So I can always calculate standard deviation out here. Formulas, insert function, right? Let's say standard deviation. In this case, standard deviation population hoga. Statistical. So this is, I'm using standard deviation population. Okay, so here I have this value here. Right?
Thank you, ma'am.
Right? Everybody good with this? Okay, so let's just take 2 minutes to really understand where do you think you can use this. I'm happy to receive all kinds of responses. If I had to find out the probability using a standard normal distribution, okay, of something that is of relevance of study in my daily life, right? It can be medical, it can be non-medical. What would I do? I can use it for anything. For example, let's say crime, right? I say I calculate statistics for murders across 100 years in a particular state. Okay, so I can always find out the average. I can always calculate the standard deviation. It's a population, it's not a sample, it's a population. And then I would say that in a particular year, okay, I find out the average, and I find that the average of, right, there is that for every population size, or for population of 1,000, the percentage of murders is, let's say, 0.5. Okay, right? So you can always say what is the probability that in a given year the probability of murders is going to be less than 0.3 in 1,000 population. Right? Use it anywhere. It's the most widely used distribution. Anybody else would like to try? You can use it for movie successes. Right? So let's say there were some 5,000 movies made on using multi-starrer actors, and you look at their box office collections. Okay, so if you look at the profitability versus the cost versus the collections, and you find out the profit of those multi-starrer. So what is the probability that a multi-starrer movie will have a success which is greater than 50% of the cost? You can do it. Anybody else? Parul, want to try? Bindu, let's see some innovation, some creativity out here. Dr. Sunil, would you like to try? Imagine a situation where you can use a normal probability distribution. Let's talk about heat. Right? Temperature. Temperature is what? It's a continuous variable, right? So you can always calculate the average temperature over, let's say, last 100 years. You can calculate the standard deviation. Okay, and now you want to find the probability that the temperature is in the month of June is going to be more than 35 degrees centigrade. Can it be done? Right, so let's say the normal average temperature in the month of June for Trivandrum over the last 100 years, okay, you've calculated it, okay, is, let's say, is around 45 degrees Celsius, and you find that the standard deviation is around let's say 6 degrees. Okay, now you want to find the probability that the temperature in Trivandrum in the month of June is going to be greater than greater than 50 degrees, right? So what will you do? 50 minus 45 divided by 6, you will find the Z score. Okay, and then because it was on the other side, it was on the right hand side, so you will look at the probability of 1 minus that particular Z score, whatever it is. So if I do it on a calculator, again, if I'm just going to share the calculator, I'm sharing the calculator. So I have a temperature of 45 degrees. Okay, I want to find the temperature which is more than 50 degrees in June. Okay, my standard deviation is 6. Okay, I calculate this. Now what is my figure that is coming? Okay, at 50, it's 0.833, so it's coming around 0.79767. So greater than 50 is going to be 1 minus 0.79767 or 0.20233. Right, so greater than 50 is going to be 0.20233. So probability that it is going to be greater is around 20%. Everybody has got the concept?
Yes, ma'am.
Okay, good. Now let's go on to the next. Okay. Okay, let me just close this one. And close it again. Okay. Now this is something called sampling distribution. Okay. Now before I go on to this, okay, I want to kind of explain to you the difference between a population distribution and a sampling distribution. Okay. Now, right now the data that I talked about, rainfall, heat, now these all basically based on population figures, where we looked at the actual population and we looked at entire population and did this. Now, most of the cases we never have population figures. If I want to calculate the incidence of anemia, okay, among women in a certain locality, in a certain age category, okay, I can't possibly go to every woman and then take the average. I would possibly do some sort of random sampling based on whatever my frame that I have constructed, and I would do a sample. Right? Is that correct? Yes. Okay. Now, typically, right? I mean, I am just telling you theoretically how these estimates or this kind of theory develops. Of course, we never really do the same process. I am assuming, okay, just to explain to you how this entire business is constructed theoretically. Okay, so assuming that when I talk about a population, okay, I looked at the frequency of a particular incidence happening. In this case, let me take an example of, can you, Dr. Sunil, can you tell me a district in Kerala which you work with?
Yeah, that's good.
Which one? Thrissur. Okay.
Yeah.
Okay. So let us say that I have taken the district of Thrissur and I have taken the incidence of anemia between girls between 13 years to 18 years. Okay, and I have taken it among rural rural districts of Thrissur. Okay, now, so obviously now I when I look at rural districts of Thrissur, I possibly will have many blocks, many villages. Okay, so assuming that on the many blocks I took, out of the many blocks, I may have taken, samples of 20 from, specific villages. Okay, now from each village, when I take a sample of 20, I would get an average anemia score. Yes. Okay, and the more number of samples that I would take, right, for each I would get a particular average. Okay, so I will have, maybe some cases I may have a, anemia. Okay, so I would find probably when I do this kind of, and I do this, multiple times, and I draw multiple samples, then maybe, I may have, I would have, let's say I do 20 samples, right? So in 20 samples, I found 5 samples had an anemia between 6 to 8. Okay, another 5 had between 8 to 10. Another 5 had between 11 to 13. Okay, another 5 had more than 13. Okay, which is technically impossible, but anyway. Okay, uh, so I kind of so what have I done in this case? I have done the same thing like a frequency distribution. Okay, because I have looked at the average of that sample, and I have looked at the number of, in that anemia range, I have looked at the number of people, number of samples which were there in that particular range. So I have done a frequency distribution.
Really, the screen is not visible if you are doing it on Excel.
Dr. Srila, I can't understand you.
Your screen is not visible if you are doing something.
No, I'm still talking to you. I'm not showing you the presentation. Okay, I'm not taking your presentation. I am just trying to first have that conversation so that you get it into your head before I show you any funny stuff on the slide. Okay, before I sometimes show funny stuff on the slide, I want to have that conversation with you. Okay, because otherwise you don't understand it. Okay, so if I do this, as I said, 6 to 8, okay, 20% of the girls had it, right? 8 to 10 anemia range, okay, another 25 girls. So what have I done? I've done a frequency distribution, right?
Yes.
Right, I've done, and it's I can convert this into a probability chart. Okay, so now what has it become? A sampling distribution. Earlier I was doing a population distribution. Now in this case, I am assuming that I have taken multiple samples, and when I have arranged the samples, I am done a sampling distribution, because I took 20 different samples and I took the averages, and then I took out the frequency. Agreed? I have done pretty much the same thing, except that I have taken multiple samples. Yes?
Madam, it would be better if you can write and as you
Okay,
speak.
let me just put it on an Excel sheet.
Yeah.
Okay. When nothing works and an Excel sheet works. Let me just 1 second. So I took, let's say, one sample. Okay, I took one sample, which is first sample. Okay, and I sampled, 10 girls. Okay, and I found that my average was 6.5. Okay, then I took another second sample. Okay, I again sampled 10 girls. Okay, and I found, right, 8. I took another third sample. Again, I sampled 10 girls. Okay, I also found 7.2. sorry. And I say I took, let's say I took, in this way I took this 20 samples. Okay, let's say I took 20 samples. Okay, now because I took these 20 samples, now in each of these cases, I would have some average. For each of these samples, I would have some averages. Let me just make this to 7 only. Okay, now let me see, right? Now let me see how many samples. 6. Now I have 6, 7, 8, 9, 10, 11, 12, 13. This is my highest. 14. Now let me just say how many are. Let me just do a. Okay. So let me say how many sample that I have of 6. 2. Okay. So I put 2 here. Okay. And let me see how many did I have of 7. I had 3. How many did I have of 8? I had 1, 2, 3, 4, 5. 5. Okay. Let's see how many did I have of 9. I just had 1. Because of 10. I had 2. Okay. So this is 20. Got this? Now what has happened out here? This has become a distribution. Okay. This has also become a distribution. Right? Now this is called a sampling distribution. Earlier we were dealing with a probability or a population distribution. Now I am dealing with a sampling distribution. Okay. Now this is a theoretical framework. Okay. Now because I am dealing with a sampling distribution, right? I, instead of using standard deviation, I use something called standard error. Okay, so when I was doing the converting into Z scores, okay, so earlier I was doing X minus mu divided by standard deviation. In this case, instead of using standard deviation, I will use something called standard error, where I will use standard deviation divided by the under root of the of the sample size to arrive at my standard error. Okay, everybody's understood this. I'm now talking to you, I'm not sharing my screen. Everybody's understood? Okay, because in real life we don't use populations, we use samples. Okay, of course many times we don't draw multiple samples. Okay, but because we are drawing a sample which is very robust, we assume that if we were drawing this sample, okay, we assume that it will be multiple samples drawn and it would, be like a, sampling distribution. It will resemble a normal distribution. Okay, we just assume this. Okay, it's not necessarily that we have to actually select multiple samples, but okay, but we assume that if the sample is done properly, the sampling frame is correct, right, that my sampling, that sample that I will draw will have a normal distribution. Now, except for the fact is that I don't use standard deviation, I will use something called standard error. Okay, the rest of the stuff is just same. Okay, so Parul is very savvy. She has got the free version and she is shared in the WhatsApp group, and I didn't know there was a WhatsApp group.
Ma'am, that's a fellowship WhatsApp group.
Yeah, that's okay. But very quick and very fast. Okay, right, but I hope that I save you the trouble of reading a lot of technical stuff.
Yeah, ma'am, it will be just for the revision. I
Yeah,
think.
so once you actually read when you attend the class, then you will kind of, it will make it easier, so you don't have to really go spend that much of time reading it.
Yes.
Okay, but everybody has got figured this out, right? The sampling distribution. Okay, so now I'm going to share my screen and then I am going to go on a sampling distribution business. Okay, now this is what we call sampling distribution and confidence intervals. Okay, now here, as you said, okay, now in a normally distributed population with a known population variance, okay, but I have taken, in this case, I am assuming that I have taken a sampling from a normally I have taken a sample wherein my population, I am assuming it is normally distributed and that I know the population variance. So if I need to convert it into standard error, you can see that I have divided the standard deviation by the under root of the sample size. Okay, by doing this, I have basically also assumed that the sampling distribution of my X bar, right? Now, why I say X bar, okay, is because you note the fact when I showed you that Excel sheet, I have taken many averages. Okay, I'm going to just, share my, right? When I looked at this, can you see my Excel sheet?
No.
Yes, in your PPT. ma'am.
You can see my PPT. Okay, let me just see my Excel sheet. Okay, now I'm sharing my Excel sheet. Okay, so if you look at this, right, so here, you have taken so many samples. Okay, all these samples you've taken. Now in this case, and each of them, there are different multiple samples that you've taken. But if I calculate the average, So my average is 9.4. So this X bar, okay, when you say this X bar, okay, is basically, right, when you say this X bar, when I'm saying sampling distribution of X bar is normal, okay. So I have taken the average of all these different samples of X, and then I calculate the X bar, which is the multiple samples, okay. That distribution is also normal. I am assuming that to be normal, okay. There may be situations, okay, where there may be a non-normally distributed population. Even then you can assume that your distribution will still be normal, provided you have a large enough sample size, okay. If you have a large enough sample size, you can still assume that. In this case, sometimes, okay, you have to do some finite uh, you know finite corrector for population, okay. So if your size of the sample is less than 0.5 of the population, okay, then you will continue using that. But if your population is, more than 5% of your population, then to calculate the standard error, right? So note this sigma x that you have said, this is called standard error, okay. This sigma error, then you have to use this finite population corrector, okay. So this is see, normally you don't have to do all of this stuff. It kind of just works out using these calculators, but theoretically you need to understand. Okay, everybody good till here? Okay, now let's just look at this one, okay. If the mean and standard deviation of serum iron values for healthy men are 120 and 15 grams microgram 100 ml, what is the probability that a random sample of 50 normal men will yield a mean between 115 and 125 milligrams per 100 ml? Okay, now in this case, it is everything is exactly the same. I am using the same Z score, okay, except what I have done, okay, I have divided my standard deviation by the under root of the sample size, because here in this case, I have taken a sample of 50. Okay, it is no more the population. So in this case, my standard error is going to be 2.1213. Okay, now here in this case, right, if you notice, I am saying I want to find the probability between what is 115, okay, and 125. Okay, and what is my mean? Otherwise it is 120. So what I have taken two Z values, okay. So 115 minus 120 divided by 2112, that is a Z value, okay, and 125 minus 120 divided by 2.112. So between the probability between minus 2.36 Z value and 2.36 Z value plus minus, okay, that is my probability of random sample which will yield a mean between 115 and 125 milligrams per 100 ml. Is everybody clear with this or not? Please ask me questions if you don't. You want to use a Z score value again? Shall we go back to the calculator? You want me to go back to the calculator?
I didn't get this concept of sample of 50 normal men. How do we?
So here I have taken a sample, right? I am basically saying, okay, in this question, what does it say? That because see, I don't, otherwise I know that, okay, fine, I have got some database or something, and I say that normally my average, mean of healthy iron levels is around 120, okay, and the standard deviation on the population basis is this, right? But let's say that I am going to do a sample of 50 people, okay. What is the probability that their mean serum levels will deviate between 115 and 125? Right? Because I am not doing, I may be having a population database, but at the end of the day, right, I need to know from my purposes that if there, okay, if I am taking a sample of 50 people that are coming in my hospital, right, what is their probability that is going to be between this and that? Okay, so that is, I'm basically trying to find on the basis of the sample, what the probability is going to look like. Okay, I have population figures, okay, but in this case I am using sample figures. Later on we will probably not get into population figures. We will only look at we'll look at confidence intervals for samples, and that's the next stage, right? I don't know the population, but I will use the sample figures to estimate the population wells, right? But this is exactly what we had done in the previous slide, except that I have just adjusted for standard error. I have now, because I'm using a sample, I have used standard error. Okay, let me just do one more. Okay, now in this case I'm using let's say means of two populations. Okay, right, you will find this example in the thing. Now here what I am doing is, like, I want to see whether or not that I have two populations. Okay, I want to see whether there is a difference between the two populations or not. Okay, I want to, let's say, I mean, this can let it be any example, doesn't matter. Okay, I want to assume that, okay, I take one block of Thrissur and I take another block of Thrissur, and I want to see whether the anemia between my 13 to 18-year-old, whether that there is a difference between the anemia levels between the two populations. Okay, now obviously in this case, right, the size of the sample that I have taken may differ. The standard deviation of the two samples will also differ. Okay, so in this case, then when you are taking this, okay, then there is again a process where you do it, where you have to combine the combined standard error. Okay, and to find the combined standard error, okay, you need to look at this sigma 1 square whole square divided by n1 plus sigma whole square divided by n2 and under root of that. That is basically, this is a correction factor if you want to find out your difference between two means, and you want to find this whether the two means are same or not same. Okay, I'm going to end out here. Okay, the reason I'm going to end out here, because too much is bad for health, right? Everybody agrees with me that too much can be bad for health. Who doesn't agree with me that too much can be bad for health? Okay, but at least I'm glad that people are being interested in the subject. None of you have run away as of yet, which is a good success parameter. No, Dr. Jagrati is laughing.
Why do we call it, ma'am, why do we call it standard error? Why do we call it as error?
Standard error, why is it called standard error? Is the end of the day, it is a deviation from the mean. Okay, it is a deviation from the mean, and therefore when you say mean, and see, at the end of the day, you want everything to converge to the mean. But if it does not converge to the mean, okay, you want to know what is the degree of variability, and that is why you call it error. Okay, so it is a technical word that is used, but yes, the question is very good. If you hadn't asked me, I would have never thought about it. See, for example, I'll take you an example of how many people invest in the stock market. Who invests in the stock market out here? Nobody? Okay, I'll explain to you, no, actually nobody invests in the stock market out here. Okay, Dr. Jagdish is saying okay. So let's say I'm assuming that the stock, I mean, for that matter, even I'm not investing in stocks nowadays. Okay, so for example, let's say the stock price is, let's say, 400 rupees. Okay, now the stock price of 400 doesn't remain as 400, like it fluctuates, right?
Yes.
Right. Okay, so when it fluctuates, right, now the normal value of, based on the, let's say, fundamentals of the stock is going to be 400. Okay, now what we say is the normal value of that stock is 400, but that value will fluctuate. Okay, that deviation, whether it is in the upward direction or is in the lower direction, it is that deviation. Okay, but over a period of time, if you kind of thing, you expect that the normal value to be there, but the fact that it deviates, there is an error in arriving at the normal value, right? So you say, you normally, when you talk about, okay, this person normal behavior is this much, is X. Okay, why is he behaving in this manner? Normally he's a good natured person. Why do you think he's behaving in this outlandish manner? Because over a period of time, you have looked at as a person behavior, and this person is, let's say, supposed to be normally very gregarious, very happy, normally very cool and something, and suddenly you find one day he's losing his temper, right? Similarly, for you may be seeing patients, okay, and you say normally this patient looks this way, and then you suddenly find, okay, why does he not, why is there a variation? Okay, so that difference, is that error in terms of deviation from the normal, is what we understand as standard deviation. But when it is done for a sample, the technical word is used as standard error, right? Because it is standardized, right? It is called a standard error, right? So most of us do not realize, but we are using a lot of statistics in our daily life without being aware of it, right? As married people, okay, right, the standard behavior of your spouse, and when the spouse does not behave in the normal manner, right, you do say to your spouse, what's got into you?
Madam, but we can't call it an error, madam. She'll beat us.
That's okay, right? So you can always say that your standard error is a little over the normal. It is not accepted within the normal standard error. Right? You can talk in statistical terms. Okay, but the point that I'm trying to make is that we think we are not using statistics, but we are using a lot of statistics without being aware of it. Right?
But
When you see,
why is it called error, madam? I mean, like, for example, when you said the analogy of stock exchange is supposed to fluctuate, huh? So you
it
can't
is
say
supposed
that.
to fluctuate, but it is also supposed to converge to the normal. But so when you say, because any deviation from the normal is
Called error.
it's an error,
Okay.
because this is what you expect it to be, right? So for example, when you take on insurance, right, you expect that normally there will be, let's say, 100 accidents per thing, and then you accordingly calculate the insurance rates.
Okay.
If the deviation is more than that, then that becomes an error, because it deviates from the what is normally expected. Okay, so normally we are all have this normal expectation level. Okay, so today, earlier we used to expect that, and sometimes you may not realize it, when we talk about our childhood, that earlier we used to have in the summer season, the normal expected temperature was only this much, between that it used to be maximum 40, but now it seems that the normal has increased, right? Because earlier we used to expect this, but because of global warming, now our normal expected temperature has differed, has our expectation level has, right? So there is a deviation from what we expected and from what is now, and that deviation is that error is in our range of expectations, and we are seeing the difference because of temperature, because what was normal and what it was now is that deviation from the normal is that error, and so we call it's technically called error, but yes, it's a deviation. And in a sample, it is called a sample standard. Standard is standard, and because normally we can't use the same term as standard deviation, so we call it standard error in a sample, right? So everybody good with this, right? Please, now that you've all got the book, okay? No, today's screen share there is error in today's screen share time lesser. Okay. Okay, so we'll end today, right? So next week we'll try and do confidence intervals, and then we'll go on to hypothesis testing, and then we'll go on to linear regression and stuff, right? So we'll do ANOVA, linear regression, multiple regression, and then finally logistic regression. And we end with logistic regression. We are going a little slow, but fine, it's okay.
Okay.
And normally I was supposed to have only 9 classes, but I don't say I'll finish in 9 classes.
Okay. Thank
So
you.
shall we? Yeah.
Thank you. We
Dr.
will
Sri,
want
your
to-
voice is not very clear.
Thank you. I was saying thank you.
Okay.
Because we are in LKG, and
No, sir, in the fetal stage only.
But what is happening with Queen's College? How much have we reached there?
and now they have given a lecture on how to look at an article, and another one on quality, how to do quality improvement. There are
Okay.
few other videos.
Okay. So this is the class where we talk to each other.
Yeah.
Okay, good. Right. Today Dr. Jagriti is looking very nice. I like the color of her sari.
Thank you. I'm going for a wedding.
Yeah, that's why I said I was trying to resist for very long.
And you are going to tell that you are going for a picnic.
I'm going for a wedding, sir.
Good. Enjoy yourself. Okay.
Yeah,
Good night,
thank you.
everybody.
Thank you. Good night. Good night. Good night. Yeah.
Thank you everyone for joining in. Thank you, Dr. Vitti. See you in the next session next Saturday, same time. Till then, everyone, take care. Bye-bye.
Bye. Bye. Bye.